Okay, so the main topic of today's lecture is Grover's algorithm, as I mentioned. And what is Grover's algorithm? Well, let me remind you of one quantum algorithm we saw, this bias-busting algorithm. What was the bias-busting algorithm? You're given as input some classical code, some and or not code that computes a Boolean function with n inputs and 1 output. And it has some enormous truth table in principle of like 2 to the n rows. And the bias-busting problem was about trying to detect, hey, is this truth table 50% zeros and 50% ones? Or is it biased? Grover's algorithm is about trying to solve the SAT problem. And the SAT problem is pretty similar. You're given like this code C that computes the Boolean function that has a giant truth table. And what you're trying to understand is, hey, is this truth table 100% zeros? Or is there at least one 1? It's a kind of similar question. So this is maybe like the most famous algorithms problem in theoretical computer science. So just to repeat, the input is like classical and or not code. Or really can be any code, because you can convert any code into and or not code. C, computing some Boolean function f. And the question is there an input string where f outputs 1? Does there exist an input x star such that f of x star equals 1? Or is f literally the all zeros function? And such a string x star that makes f output 1 is called a satisfying string. It satisfies this code, and that's why it's called SAT. And another small thing is I'm going to be talking, C and f are basically the same thing. Like I'll use C to mean like the actual source code and like f for the function it computes, but it's not going to be a very big deal. Technically, this problem in theoretical computer science is actually called circuit SAT, but like circuit SAT and SAT are basically the same thing. It's the canonical NP-complete problem, as I hope you learned in 251 or some such course. And so it's a very hard problem, seemingly. So what is known about algorithms for this problem? Well, there's a baseline algorithm, which is the brute force algorithm, which is literally just try out all possible strings. And I guess the intuition here is that, like, you know, if you've ever seen source code C that some terrible person wrote, it can be extremely hard to understand how it works. So, like, you could be like, think, oh, I'm going to be smart and read this code C and try to figure out what it's doing and try to figure out if it outputs 0 on all inputs. But some code is just like so obfuscated that you're like, I have no clue what this code is doing. Now, one thing you can always do is just run C. You can be like, I'll give some inputs to C and see what it prints out. Like maybe it'll output 0 or maybe it'll output 1. That's always easy. Even if you don't know how C is working, you can always just run it. So the baseline algorithm is to just literally do that for all possible inputs. Let's try all 2 to the n strings x. Okay, if n is bigger than like 40, then this is probably a bad idea, because 2 to the 40 is an extremely large number. Well, I guess that's only a million, that's a trillion. So 2 to the 40 is okay, but if it's bigger than 70, that's extremely bad. So how long does this algorithm take? Well, this is the bottleneck, 2 to the n strings. A small feature is that you also have to run this code, C. But, you know, somebody gave you C on a, you know, as input, so it can't be that big. Let's say that has like m lines of code. So then, so the time this takes is basically 2 to the n, well, maybe times m. I don't know, put a big O in here for safety. But in some sense, like I really, you should try to have in mind actually the case that like n, the number of variables is like 1,000, which is a lot, because you know, this code comes to you as like an input. Like it might have like a few thousand lines and a few thousand variables. That's a very normal size for an input. And this just goes to show this is like a terrible algorithm in the sense that 2 to the 1,000 is, you know, longer than the age of the universe in attoseconds or whatever. Another thing to have in mind is I'm going to mostly just like write this as like approximately 2 to the n, because usually you could imagine this is like 1,000 or 1,000,000 or something, which is like 2 to the 10 or 2 to the 20. But if this is like 2 to the 1,000 or 2 to the 2,000, this part is negligible. So basically, don't worry about this minor factor, or you can imagine that it's at most n squared or something. But basically, this brute force algorithm takes 2 to the n time, even more than 2 to the n time. Okay, so is there a faster algorithm? Well, people have been thinking about the question of is there a faster algorithm for like, I don't know, 50 years at least, and nobody knows one. So basically, nobody knows an algorithm faster than this. So it's like a 50-year-old fact. No one knows, let's say, big O of 1.9999 to the n time algorithm. That's kind of sad. And, maybe the most famous unsolved problem in mathematics is the P does not equal NP conjecture. And this P does not equal NP conjecture is literally equivalent to saying there's no polynomial time algorithm. There's no poly-n time algorithm. You might honestly say, hey, this is a pretty weak conjecture, because we don't even know 1.9999999 to the n time algorithm. And this is just saying, wow, there's no like n cubed time algorithm. So that's definitely believable. In fact, these days, a lot of people in complexity theory talk about Seth. Seth stands for strong exponential time hypothesis. And it basically says it's the hypothesis that there is no order 1.999 to the n time algorithm for any number of nines. So it's basically the conjecture that says like you really can't do anything better than brute force. And this is a far stronger conjecture than P does not equal NP. I like to think that every reasonable person believes this one. I also believe this one too, but since it's much stronger, maybe you can waffle on it a little bit. But point is, in 50 years, we don't know how to break this conjecture. Okay, so that's SAT. There's a lot of variants on SAT, and all these variants on SAT are more or less equally hard. I alluded to before, there's like some difference between like circuit SAT and CNF SAT. But here's a couple of more variants. One variant is, in this problem, you're kind of trying to tell the difference, like either like there are no satisfying strings or there are at least one satisfying string. A slightly easier problem, maybe, would be if you somehow magically knew by a promise that either there's 0 satisfying strings or there's exactly one satisfying string. That could be easier. That's called unique SAT. Although, intuitively, probably not really that easier, because the whole difficulty of the problem is that there could be like very few satisfying strings, and like it's, if you just start picking random input strings, you're not going to find one that makes the function 1. So somehow the case where there's exactly 1 out of 2 to the n satisfying strings kind of seems like the hardest case anyway. You can make that formal, and so it is true that these two problems are equally hard, basically. Another very natural problem is the search version. This is just the problem where it's like you have to say yes or no. Is there a string that satisfies the code C? It's pretty natural, like if you have an algorithm like that and it comes back and it says yes, there is such a string. You kind of want to say like, why don't you tell me such a string then? So that's the nature of the search problem. In the search problem, like the algorithm to be correct, it either has to say, hey, there is no such string that satisfies F, or it has to say there is one such string and here's one such string. That seems maybe harder because you have to do more work, but again, you can show with polynomial time reductions that it's just equally hard. It's not really more hard to require the algorithm to find a satisfying string. And because it's convenient for Grover's algorithm, which is what we're going to talk about, because it's convenient for Grover's algorithm, we're going to look at like a combination of these two ideas, this unique idea and this search idea. We're going to kind of put in like one thing that makes it a little bit harder and one thing that makes it a little bit easier, but actually it's all equivalent. So I'll call it unique sat search. And this is, you're somehow promised that there's exactly one satisfying string, no more, no less. So there's, this is not great, a unique satisfying string x star. And the task is to find this x star. Okay, so on one hand, it's a little bit easier because you don't have to worry, like, maybe there is no satisfying x star. I'm like, no, just take for granted that there is one, exactly one, but you have to find it. And it seems basically equally hard, and in fact, provably, it's basically equally hard. Because, if you don't try to, like, analyze C, and you're like, the only thing I can really imagine doing is, like, running C on different inputs, then it's basically like you're trying to find this 1 out of 2 to the n needles in a haystack. Okay, so what we'll see today is Grover's algorithm, which solves this variant of SAT in like 1.4 to the n time, or more precisely, square root 2 to the n time. And, well, it's still exponential time, but it's less exponential time. We'll reflect on that a little bit later. Okay, before we go on, let me just try to convince you, in case you're not already convinced, that SAT is a really important problem. I mean, if you remember, like, complexity theory or 251 or so forth, and you remember, okay, it's the canonical NP-complete problem. That's pretty good. But I just want to say it's like a problem that you would really, truly, genuinely like to be able to solve efficiently if you could. So over here, like, I put 4 example blocks of code, 4 possible inputs to the SAT problem. And just imagine how great it would be if we had an algorithm that we could run on these 4 blocks of code to determine if they're satisfiable or not. Or maybe not determine if they're satisfiable, maybe also find satisfying assignments. So, just for fun, let's look at them. This code takes as input 1,024 bits. And it treats the first half of the bits as like a number in base 2. It treats the second half of the bits as a number in base 2. Then it like multiplies these 2 numbers, calling the result W. And then it checks basically if W is this certain 309-digit number that's like hard-coded into the source code. And I think I got this wrong. Let's say 1, 0. And if W does equal this number, then it returns 1. Otherwise, it returns 0. So that's crazy. So what is a satisfying string for this block of code? Well, a satisfying string for this block of code is like a string that makes it return 1, which is basically the encoding of 2 integers that multiply to this particular 309-digit number. And this particular 309-digit number is called RSA 1024. It's called 1024 because it's this many bits. And it's like a famous factoring challenge number. It used to be that you would get $100,000 if you could come up with the prime factors of this number. Nobody could do it, and after a while, they're like, let's cancel this competition. But as you probably know, like factoring is very important for cryptography, and we kind of are assuming that it's very challenging to find a satisfying input for this number, because that's equivalent to factoring this number. Yep. Yeah, so this is not really a proper answer of unique SAT. This is just an instance of SAT. Actually, it's convenient. You could make this unique, probably, assuming this doesn't have more than one kind of prime factorization. You could throw in and y is less than z here. And then this would make it actually not just that this has a satisfying assignment, the factors of this, the 2 factors of this, but has a unique satisfying assignment. But in the remaining ones, I'm not going to worry about uniqueness. But this is actually a kind of cool one where you can cook things up so that you're sure there's a unique answer. Yeah? Yeah, they got this by choosing two 512-bit prime numbers randomly and multiplying them together. So that's actually why factoring is so important or used so much in cryptography, because there's an efficient way to generate the hard puzzles. It's not just like, oh, this problem seems real hard, I don't know how to solve it in general. There's this extra bit where like, I know how to randomly create hard instances of this problem. And for factoring, it's really cool. How do you make hard instances? You pick two gigantic prime numbers, you multiply them together, and you hand out the product and say, try to factor this. But you yourself know the solution. So that's why it's a cool puzzle. It's literally basically one of the only problems anybody could ever think of that had this feature. Hard to solve, but easy to randomly generate hard-seeming instances. And that's why like everybody in cryptography is obsessed with factoring for like so many decades, because it's like the one problem basically we know that has this feature. This is a kind of a crazy one. This thing is called a block header, I think. This this C takes in like 32 bits and like adds it to this, I don't know, fixed number. Then it takes like a SHA hash of that. Then it takes a SHA hash of that. And then it checks if like the first so many, 64 bits of this hash are all zeros. And if so, it returns 1. And this is exactly, I guess, what's going on in like Bitcoin mining. Like you're trying to find like numbers, which when you like hash them twice, basically the first 64 bits are all zeros. So like if you could have a SAT solver run on this block of code, which is like 2 lines long, and it'd be like mining Bitcoin for you as fast as you could. Here's another one. This one's, I'm not going to explain this one too much, but like this code takes in like 10 megabytes of bits. And maybe it interprets these bits as a candidate proof of the P does not equal NP theorem, like written down in some mathematical language. And there's a very popular mathematical proof checker that's used a lot today called lean. So basically, you can pass lean a string that's supposed to encode a mathematical proof, and it will tell you whether this proof is valid or not. So a satisfying assignment for this block of code, we have to build lean's proof checker code into it. A satisfying assignment is a mathematical proof that P does not equal NP. So if you had a SAT solver that could find satisfying assignments, it would like find a proof of P does not equal NP, assuming there is one that's less than 10 megabytes long. That's pretty cool. This is like my last example I thought of. This code takes in like 1 billion bits, and uses them as parameters in a neural net, and computes this neural net's training error on some fixed training data, and it returns 1 if and only if the training error is less than 0.1%. So then, if you had a SAT solver that was really good, you would plug in this block of code, and it would just like auto-train your neural net. It would find all the parameters, lickety-split. Yeah, so this is all just examples to show you it would be really, really awesome if we had like an efficient algorithm for SAT. Well, we probably don't. Okay. But let's see what quantum can do for us.